Hey, welcome. This is Jake Williams from Edition InfoSec. We're going to do today a little bit of introduction to malware reversing. Right? Now, a couple of things right off the bat. Right? You're seeing the desktop of my Windows virtual machine that I use for malware. You'll notice the desktop background is super unique. Unique in that it's bright orange. Almost like the, if you ever grew up in the country, I certainly did, you know that when you're out hunting, you wear blaze orange, right? So somebody doesn't shoot you, hopefully at least. Actually, where I come from in the mountains, I say mountains, Blue Ridge and Appalachian area of Virginia, very often we have folks that will spray paint using bright orange paint, the word cow, on the side of their cows so they don't get shot by drunk hunters, right? So kind of the same thing's going on here, right? We want a bright background that immediately distinguishes, at least for me, immediately distinguishes the difference between my regular desktop working environment versus my virtual machine that I have, malware in, right? This stuff is difficult enough to keep control of without endangering, creating all kinds of problems. Let's just go there. So what are we going to cover today? All right. So we're doing a very basic intro to malware reversing. I don't have time to cover everything, obviously, right? So a couple of things we're gonna do here. Very abbreviated, very abbreviated course, very abbreviated kind of session. We're gonna walk through just a couple of high points. I want to really whet your appetite for this, right? What I'm not gonna do is I'm not gonna do the standard trope of let's run Redshot and Procmon and maybe Process Hacker. I love doing this, right? But I feel like we want to go a little bit beyond, maybe not a little bit, let's go just beyond where we would ordinarily stop with a sandbox type tool, right? So sandbox type tool will detonate the malware and we'll run it under a number of conditions. Now, that's not to say that we should never need Redshot and Procmon and those other tools, but I prefer to get something a little bit more in depth. I prefer to find some things that maybe my sandbox tool wouldn't otherwise pick up or wouldn't otherwise see, right? Let's get it on then, right? First thing we're going to do here, and by the way, you'll be provided a download link for these samples, sample 1, 2, 3, and 4. Now, I have to tell you that one of these samples is one that was passed to me. I'm not convinced that it's malicious, right? Now, and I'll mention which one it is as we begin some of our analysis. But I'll tell you that's actually a very common thing that we deal with, right? When we begin threat hunting or doing incident response, very often things are passed to us as malware reverse engineers that may or may not be malware, right? And very frequently, the may or may not ends up being not. It's just not malware, right? So how do we identify that? Well, let's start out by walking through some of those techniques. Now, before we do any of that, right, I would be remiss not to mention that don't do this on your host machine. I started by talking about the orange. I was like, man, use orange, right? And I do, or something that's distinguishable to you. My regular desktop doesn't look this way. It's got the nice rendition logo, and that's my regular desktop. This is not. This is very distinct from that, and this helps me avoid not dragging and dropping malware onto my onto my host machine. Now, look, best practices would indicate that you should always study malware in a basically on a dedicated host machine. That you're because of course we have hypervisor escapes. I'll just mention your hypervisor escapes are exceedingly rare. I've looked at this malware or suspected malware before. I'm convinced none of it has a hypervisor escape. I feel pretty confident. I say convinced. I feel confident. Run this at your own risk. Again, best practices state that to protect against a hypervisor escape, this should be a dedicated host for looking at malware. Second thing, I have a clean snapshot. So the state that we're in now, I have a snapshot that I can revert back to. If you don't have VMware Workstation Pro, I highly recommend that. VirtualBox, a lot of people talk all about VirtualBox. And like, man, you can do everything you can with VMware. Listen, I've been around for a while. I've done a lot of this stuff in the past, and I'm just going to tell you, I've never been impressed with VirtualBox, right? For lots and lots of reasons. But the TLDR here is malware reversing is hard enough as it is before I get into dealing with dealing with weird virtualization problems. VMware has my back. VirtualBox has less than a single FTE, working at numerous security vulnerabilities that are open, and I'll just leave it there. Anywho, call that for whatever it's worth. I've gone to VMware Workstation Pro more for usability, honestly, than security. But also here, this is a Windows 10 X64 virtual machine. I have it set on my trial mode, don't really care one way or the other, but as far as that goes, I don't need a licensed, I say a licensed, obviously if I'm using it for an enterprise evaluation, I am of course evaluating the stability of the software. My point here is you don't need a fully licensed VM to do any malware reversing. You can certainly use one of your trial VMs or an enterprise trial to do so. Right. So the final thing I'm going to mention here again is certainly practice good drag and drop discipline. Have a good snapshot. Practice good drag and drop discipline. There are malware reversers who have accidentally drag, dropped, and executed malware on their host machines, and there are those that haven't done it yet. Right. So I'm just going to go ahead and tell you that in most cases people will go ahead and do this eventually. Anyway, so please practice good drag and drop discipline. I haven't done it for this, but I will tell you that one of my secret weapons in avoiding this, and it's something that I do in my most of my classes that I teach, is I will actually change. If you note here as we go into the sample, I'll change to EX $. Right. Now the reason that I do this is you'll notice the icon goes away. Right. Now why is that? Well, the actual icon that we have there, if there's an icon at all, is embedded in the resources section. And if the file extension isn't an executable file extension, even though it is an executable file, we haven't changed the file itself, we've only changed the extension. If the file is a executable extension, then it'll go ahead and process it. Explorer will go ahead and process the resources section, grab the icon, and go ahead and populate it there. We don't have that here, right? So okay, so I'm going to take that off there, sample exe. But again, just know that that's a way that I can avoid worrying about double click, because there's no double click handler for EX $, whereas the Windows loader, basically the setup there is EX, the exe Windows loader is going to go ahead and take that and run with it, right? So it's okay. The first thing that we want to do here is do some basic metadata analysis, and I'll tell you that one of my favorite tools for this is PE Studio. I'm also going to show you Cff Explorer, but these are two things that I do before I start any other analysis. Now, I also want to be very clear here. Again, I'm not covering soup to nuts malware reversing, right? This is a very short class. This is an intro, and hopefully is going to give you some ideas for some actionable things that you can find. So what I'm going to do here first is I'm going to drag sample1.exe onto PE Studio. PE Studio is kind of my expert knowledge system. The way I describe it is my expert knowledge system basically for malware reversing. Now, you'll notice here that it has a virus total score. That's because I'm online, and it is indeed querying out to virus total. If this is a security issue for you or an OPSEC issue, either disconnect your VM from the net, and honestly, for best reversing when you go live analysis, you should probably disconnect this from the net because you're making calls out. But again, if there's an OPSEC issue here, by all means, certainly disable that feature, or you can disable your network, or you can go in, and I feel like there's a config box someplace where we can change that. I just don't remember right off the bat what that is. Anyway, so it's going to go out and take a look at what's there, what's not. Now, of course, this is going to take a second to process, but as it does, I want to look at a couple of things here, right? So a couple of things right off the bat here. One of the things I like to look at here is what is the compiler timestamp, right? Now, this may or may not be super interesting to you. One of the things that we find is that some attackers will backdate the timestamp. You may be familiar with time stomping. They may backdate the timestamp on the system, based on the file system, but then they leave the compiler timestamp. Well, this is an embedded timestamp in the executable. We also occasionally see what we might call vanity timestamps in the compilation timestamp. And a vanity timestamp, or an example of a vanity timestamp in action, would be the Ukraine/Russia lights out attack, right? So when when Russia took Ukraine offline with the lights out attack, they actually used a custom goodness, timestamp there. I'll tell you, I didn't really make a lot of it, right? I did some analysis. I may have been the first to publish on that one in particular. I'm not sure if I was. I haven't seen anyone else that published on it before, but in any case, I'll just mention there that that was one of the things I found really interesting about it, is they had intentionally backdated the timestamp, and backdated might be an interesting word there. Right? I might even go so far as to say, rather than backdated, maybe the way to say would be that. Would be that instead of backdated, they modified specifically, and in this case it was backdated, but it was modified, and then we step back and say, okay, well, why? What is significant about this date? And as we did a little bit more analysis, we found out that indeed this was the date that was used was actually a date when some Albanians were fighting some, basically an Albanian security guard was killed in basically protecting a substation, power substation, right? So you tie that with like lights out, and it was kind of sending, we think maybe sending a coded message. It could be that. I mean, it could be any number of other things, right? There's only 365 days in a year, and of course, if we're taking the year out, right, that creates more collision attacks. In any given day, though, lots of stuff happens that may or may not be significant to us. Did the intended target get the message, or was it even a message? Was it just random, and I'm inferring something from nothing? Hard to say. Bottom line, I'll mention that this is a useful, we find this to be a useful tool to use. Sometimes, again, I'll mention that sometimes I'll mention that as we're performing these analyses with the basically with timestamp analysis, that we'll find that a particular post compilation tool is modifying the timestamp, so it's something static, right? We've seen that in the past. In any case, take a look at this, right? It's something a lot of tools don't pull out, and it's something that you probably want to see. Now, a couple other things that I want to take a look at here. Right off the bat, we have this indicators tab. Now, some folks will say, hey, why don't we look at these indicators? What are these? How important are these? And look, the reality here is these are purely expert knowledge pieces that the creator of PE Studio has said, hey, look, this is the kind of thing I look for. So for instance, here, the file references the URL pattern. The URL is 127.001, right? We've seen that basically you may have noticed as we went in to the executable. A second here. So just went into the executable. You might notice a little UAC check mark there. And that UAC check mark, of course, means that the manifest says go run that as administrator. And you see indeed that there, right? And that's another one of those spots where, is that necessarily malware? Does it mean it's malware? No, none of these mean that any of this is malware. What it does mean is that these are things that are very typically seen in malware. And the way that I like to note these, or the way that I word these, is I say, hey, these are my malware gang signs, right? The idea there being that a single one of these isn't going to make me go, oh my gosh, right, kind of thing, but enough of them together are going to convince me that indeed something is amiss. The way that I kind of word this is, or the way that I explain this is sharing an experience. I grew up in the country, largely in the country, and backwoods of Virginia, and after joining the Army sent me TDY out to Los Angeles. I'm a whopping, I believe I was 21 years old at the time, 22, something like that. Land in Los Angeles, and like a good farm boy, I'm wearing a red bandana to keep the sweat out of my eyes. A gentleman kind of stopped me in the taxi line and said, hey, that does not mean what you think it means here. I can tell that you probably are ignorant of that whole red bandana thing. Now, mind you, as I talk about this too, this is in the 90s in Los Angeles, right? So Los Angeles is a very different place today than it was then, and I'll just leave it there. Alas, the reason I suspect he felt comfortable coming up and saying, hey, that's not what you think it is because I only had one sign, as it were, right? If I had other things that might typically be equated with that type of behavior, maybe a couple of teardrop tattoos, on my face, maybe some other gang paraphernalia, and some maybe you can see that I've got a pistol stuffed into my sideband. Those are all things together that individually might not mean a lot, although the teardrop tattoos, let's be fair, are pretty damning. Combine that all together, and maybe then we now have enough to say, hey, that now together is suspicious enough that we want to take a deeper look at. That's really what these IOCs are, these indicators. Now take these for whatever they're worth. If you're brand new to malware, I highly recommend you take a look at PE Studio and kind of take a look and say, why? Now you're going to use Google at this point and say, why did they identify these things as potentially malicious? This one's a great tab to take a look at here, libraries, right? And I want to talk about this for just a minute before we continue on. Each one of these DLLs is imported by the malware. Each one of these DLLs does something for the malware, provides some functionality from the operating system to the malware, or should I say to the executable, right? Because we've already determined that and identified that this may indeed not be malware, right? This one is. I'll just go ahead and throw it out there. You can see 37 out of 70 of, look at this negatively in virus total, and for whatever it's worth, it just is malicious. That said, why are some of these in a blacklisted or blocklisted? I think is kind of becoming the more appropriate term there. But why are these blocklisted, right? Why are these identified as potentially bad? Now, look, all of these, each one of these is a Windows DLL, right? So I have to throw out here and say it's a Windows DLL. It must. There has to be. We can't just say, "Oh my gosh, it's negative. It's a bad DLL." If it's a Windows DLL, the reason they throw these out here is these are very frequently seen being used by malware. One important one that I want to mention here, or actually two important ones. WS2_32.dll is WinSock, right? So the WinSock DLL. This is what provides us low-level socket access, right? So if I wanted to do any TCP or UDP, I would use WinSock WS2_32.dll to perform that action. Now, you can imagine most malware has command and control, hence most malware needs networking, hence WS2_32.dll is one of the interesting DLLs that we should at least be interested in taking a look at, right? Okay, so what next? WinInet.dll, right? WinInet.dll actually provides a superset of the functionality, maybe superset, that's the wrong way to word it, more advanced functionality than WS2_32.dll. Now, anytime you see WinInet loaded, you're going to see WS2_32 WinSock loaded as well. WinInet actually provides HTTP, HTTPS, FTP, and Gopher, right? Yes, Gopher. Believe it or not, Windows, Microsoft has included Gopher all the way up through Windows 10 and Server 2019. In fact, I'll show that to you in just a minute. It's absolutely wild that that's still there. But alas, what do I expect then? Well, I expect by seeing this immediately, before we've gone any further, I expect this is using HTTP, HTTPS, or FTP as a command and control protocol. Now, could you use HTTP, let's say, or FTP without WinInet? You can, as it turns out, but you would have to conduct or construct all your protocol headers using the low-level functions in WinSock. But most attackers don't want to do this. Honestly, the easy button is using the WinInet functionality anyway. And you get another benefit here, and that benefit is that you get to automatically use the victim's proxy settings for free. WinInet just communicates across that proxy. Ever notice in Windows, when you go into the Internet Explorer settings and you change your proxy, like everything else just magically knows how to get out to the internet? Well, that's because there's a single proxy setting. It's WinInet. Now, certain applications can use their own separate proxies, dedicated proxy configs, but generally it's a single proxy configuration, and again, that's controlled through WinInet. Right? So got a bunch of other DLLs here, but I just wanted to highlight here, this is a great spot where I don't want to call these false positives, right? There's a reason that every one of these is called out, right? And again, by all means, Google, and what I would Google is not what is urlmon.dll, but how might malware use urlmon.dll, for instance. I'll tell you, with urlmon, it's almost certainly an API called URL download to file. URL download to file does exactly what it sounds like. It is the easy button for attackers to go drop additional malware to the machine. Now we're going to go a little more granular here by clicking on the Imports tab, because in addition to having the basically the DLLs loaded, all these DLLs export functionality, and we've now imported that functionality. And you'll notice here, I'm going to go ahead and sort on the blacklist or block list, however you want to word that, and you can see some of these API names, right, that have been mounted here now, or sorry, mounted, excuse me, that have been imported. Now, I'll mention here that anything you see imported is imported for a reason, right? We know that it's going to be used in the malware in some capacity. We don't necessarily know what. That's what our job as reverse engineers is to do. Now, there are some of these imports that we are basically that how do I want to word this here? Some of these imports that we may not see executed in a given, basically in a given run of the malware. This is a problem that we have with sandboxes, right? So if, let's say, for instance, I have a piece of malware and that malware only executes a particular piece of functionality, let's say stealing contacts, when Outlook is open. If my sandbox doesn't have Outlook open, doesn't have Outlook at all, Outlook installed, or Outlook running, then we're not going to see that particular functionality. That's one of the reasons that I'm starting with this with PE Studio, because this is what we would call a static properties analysis, right? So a static properties analysis, we're able to come in and see basically the functionality available. Now, you'll notice here that even though these are blacklisted APIs, they are not necessarily malicious APIs, right? For instance, regsetValueX, right, EXW, by the way, the W stands for wide character, and an A stands for ASCII, right? So a lot of these APIs that take a string argument have both an ASCII and a Unicode, a wide character, equivalent, right? So just maybe bear that in mind, right? Or regsetValueX, obviously not malicious. We set values in the registry all the time. So why is this one marked as malicious? The answer is, well, it's very often seen used in malware. Just likewise, get host by name, right? Get host by name is literally just a DNS lookup, effectively a DNS lookup, although it's not always DNS. If it's in the resolver cache or the host file, that certainly takes precedence. But you get the idea there. Basically, resolve. Oh, sorry, that was get host by value, not by name. Anyway, so regardless here, basically wanted to highlight here that this number over here, this 52, this is what we call an ordinal. And basically the DLLs they're basically exporting either by name or by the position in their export address table. So if you picture an array, basically that's all you have, a table with a bunch of entries in it. They're saying go grab element number 52. So this is a way to get a little crafty. Microsoft does a lot of this importing by ordinal because they don't publish the names for a lot of their internal functions, and they don't because they don't have the names published. There's no way to then go look that export up by name, right? So now in this particular case, these are well-known ordinals. It's a fairly rare thing, by the way. Outside of Microsoft system software where they have these internal use only APIs, it's fairly rare for software to import by ordinal. So the fact that that's happening at all here tells me, it certainly kicks off some malware gang signs. But let's talk about a couple of these APIs as we go. We've got certainly the basically get volume information. Sometimes this is used as an anti-debugging type tool or anti-analysis tool. So for instance, get volume information will tell you things like what is the size of the volume. That obviously could be interesting. Certainly the serial number of the volume. VMware does some very interesting things with that. And so there's a few different pieces we can use there to identify or get volume information. And that could be it. It could just be a system profiling tool. We don't know that yet, but I'm going to think about that a little bit. I'm also going to note here the control service and delete service, right? So what services is this? Deleting? We don't know yet, but certainly I want to think about that and keep that really in front of mind. That indeed there's going to be potentially some service deletion. Notice here a call to a resource, lock resource. Resources are embedded into the binary, and so with that lock resource, we might have some data being dropped, etc. Right? A couple other things. I know that I expect it to set and possibly delete values and keys. So setting values, probably persistence, deleting values and deleting keys. That's interesting. We want to take a look at that, certainly. We also see here good old URL download to file, right? Exactly what we expected. We also see some Internet Connect, right? There's an Internet read file. This is where we read the data back for command and control, so certainly interested in that as well. The reason I'm bringing this up here is that if I run this in a sandbox and I don't see, for instance, setting a registry value, I haven't seen all the functionality that the malware has, right? Write process memory, this sounds a lot like code injection to me. Read process memory sounds a lot like possibly hooking, right? Which may go hand in hand with code injection, right? So I'm kind of looking around that. Notice here I said hooking, and sure enough, what do you have here? Call next hook, set Windows hook X, and unhook Windows hook X, sometimes used for anti-debugging, but very often as well used for keylogging, right? So we have things here like move file. This one's interesting here, find first file and find next file, right? So these are basically doing directory listings, right? Now, as I start putting all this together, I want want you to think about this, right? We've got all the tools used for command and control. We have something that wants to run as admin. We have something that is doing cross-process modification with write process and read process memory. We have basically directory listings. We have deleting services. If I combine all that together, is it possible that a legitimate tool, remember I said one of my first jobs is it malware or not, right? I said one of my first jobs there is figuring that out. I'm going to go ahead and call this probably malware, right, based on all of these different malware gang signs. Creating additional processes, process 32 first, right, as well as process 32 next, is going to walk the process list. I've got a lot of things here that look really bad. Terminate process, one final one that I'll mention. This reaches out and kills a remote process, right? So again, as I put all this together, are there legitimate tools that need this? The answer is sure, there are, but they're probably few and far between, right? So I should go in with the expectation that this indeed is probably malware. Final thing, I say final thing, let's do a couple more things here. I want to go take a look at my strings. Now, you won't always have this. Some malware is packed, a lot of malware is packed. I very intentionally grabbed some samples here that aren't packed because we don't have time to go through how to deobfuscate the malware or lots of different malware types and packer types to get in and do analysis. So I wanted to do something where we could get you up and going quickly. And I'll mention too that some malware isn't packed, right? This is kind of one of these things that cycles back and forth. Where some antiviruses will penalize in their heuristic scoring anything that's basically anything that's packed, right? And so when that happens, we see kind of that float back to let's not pack stuff, right? In any case, here you get an idea of some stuff that's here. I'm interested in all these strings that are these ASCII strings. What are these specifically? I don't know yet, but certainly we'll put that all together, may work all that out. And so as we start looking around here, again, just some of our strings. Again, just want to kind of throw this out around here. Uninstall. Here's our current version run. Grandma, God rest her soul, knew all about the run key. All right. By the way, here, very interestingly, you may notice here that there's two versions of the run key. One of them says WoW64 32 node. Now, what I want to mention here, by the way, is that with this WoW64 32 node, basically what you're dealing with here is the Windows on Windows 64 subsystem. WoW64 allows you to run a 32-bit. Basically allows you to go run a 32-bit executable on a 64-bit subsystem. Now, because there may be issues between configurations, let's say for a 32-bit software installation and a 64-bit software installation of the same name, there's a separate software hive for 32-bit, right? So anything running that's 32-bit is running in WoW64, and when it queries the registry, it's going to do so out of Microsoft, out of the WoW64 32 node. I'll demonstrate this real quick here, and then we'll get back to moving. I've got my command prompt here, and then I'm going to go grab one other command prompt, and let's do a C Windows syswow64. syswow64 and command.exe. Right. So notice up here, one of these says says syswow64, the other says system32. But notice that, and I'm going to go ahead and change directory over here to Windows system32. I'm going to dir calc.exe because it's, let's be fair, right? Anything in security has to pop calc. We'll go ahead and dir calc.exe here as well. Now listen, I don't need any fancy hashing software to see these are different, right? So 27648, 26112, but notice they're both in System32. What's going on here, right? Well, the reality is that this is actually really the one in syswow64, right? But we're doing file system redirection here, right? So there's a file system and a registry redirection done in WoW64, right? So if I come back to my basically my 64-bit version, if I say dir .syswow64 calc.exe, right? Now we see the 26112, it's the same thing, right? Let's do a quick registry query since that's how we started originally. So reg query, right? So reg query, HKLM, software. I'm just going to copy this because I'm a lazy typer. You've already seen some of my miraculous typing already. Notice that these two things are different, right? But you'll notice down here at the bottom, in my 64-bit version, I have a WoW64 32 node. All right, now you'll notice that some of these things are identical, right? I've got, let's see, do I have something for Python in both? I don't. What do I have that's in both? There's some stuff in both, and I'm just going to call it there because I'm sure. Let's see, Microsoft, Mozilla plugins, right? So we've got a couple, ODBC, right? There are a few of these that are identical across both, but most often not so much, right? Now, if I want to see the WoW64 32 node here, I can literally then query that. Okay. And you'll notice here these are identical. Why is this of interest to us? Well, if I've got a 32-bit malware sample and it just specifies the software hive, right, it's going to then query the software hive under WoW64 32 node. The fact that this is here at all tells me that this was at least identified as, the sample was at least considered, or the running of this on a 64-bit system was at least considered, right? You'll notice here as well a bunch of select statements. These are not SQL, actually, as it turns out. This is, let's see, it's Windows Query Language or Windows Hardware Query Language, something along those lines. I think it's Windows Query Language, if I remember correctly. Runs a lot like SQL. Basically, the idea here is that they're grabbing data, probably for profiling the system, but not 100% sure there, right? So, like, for instance, grabbing the processor and the video controller, sometimes is used to identify virtual machines, and then just not run in those sandbox environments, right? So I'm not 100% sure there. Out.txt, I want to take a look at do I have an out.txt file? That kind of stuff, right? So again, that's what I'm starting with the strings here, right? This is why I'm starting with static properties analysis. By the way, with these strings, I have a strong suspicion that this is a base64 encoded. Thanks for that, Google. Base64 encoded. Basically file that's basically jammed into. And by the way, the base64, you'll notice here a base64 alphabet. If you're not familiar with base64, the default base64 alphabet are the capital letters, lowercase letters, 0 through 9, the plus and the / sign. So I'm kind of, I'll shoot in the dark here. By the way, too, also looks like there might be a batch script being dropped. We don't know that 100%, but fairly reasonable assertion. So I've got a few things that I'm going to be looking for as I start the static properties analysis. By the way, I'm typically then also going to I'm also going to start taking notes about what should I be looking for, right? So I'll typically have a notepad up, and then the what should I be looking for as I go into dynamic analysis. We're not going to do all the dynamic analysis or the runtime analysis. We're going to walk through a couple of different samples here and roll there. A couple other things I want to note here. As we get in, basically right off the bat, you can see, again, we're looking at a 32-bit executable. I showed you the compiler timestamp already. Let's take a look here at my sections, right? So with my sections, you can see the individual names of the sections. These names can be anything, and you may have more than 4 sections. You may have different section names. By convention, .text is the code, right? And of course, the code is going to be marked as executable. And our data section, as you can imagine, will be marked writable. It's rare to have one that's both writable and executable, as I'm sure you can imagine. .rsrc is the resources section. One of the things that we're looking at here, a couple of things we're looking at right off the bat, one of them is entropy, right? So basically this is a measure of randomness in bits per byte, right? So higher is higher entropy, right? So a higher number approaching 8 is a higher entropy. And when I see a high entropy, a very, very high entropy, and by the way, a high in a scale of 0 to 8, high is like 7.8 plus, right? So if it's better than 7.8, I'm typically going to be a little suspicious of it. Something I'm going to want to take a harder look at, right? So 7.8 plus, I'm going to suspect that sample then is packed, and we'll likely take a hard look at the sample. Right? Okay, so 7.8 bits per byte. None of it is that. I don't think it's packed. I mentioned already it's not. We see a lot of strings, and we're not going to get into how to unpack malware here because again, just time and space. Right? Okay, so .text section. Again, is our code. .data section, again, data. Resource, iData typically is imports. And then the RSRC, these are resources section, right? So this is any arbitrary data that we need to jam into the executable. We oftentimes see additional executables packed here. And I'll go into the resources here in just a second. But before I do that, I want to mention here that we have section hashes, right? Now, what are section hashes? Well, what's happening here is that PE Studio is going through and it is individually calculating on a per section basis the hash, the MD5 hash of the executable. Now, some folks are like, MD5 is old, right? Yeah, it is, but it's fast, right? And hash collisions here don't really happen, right? When we talk about is MD5 too old to use, really we mean that from a security standpoint. A hash collision here doesn't hurt us, right? As opposed to like in a certificate where a hash collision undermines the entirety of that security control, right? Of that security mechanism. So here we do very much not care about hash collisions, whereas in a certainly in another environment, we would care a little more. Again, like a certificate-based or certificate authentication, something along those lines. Basically, though, with this hashed value, I want you to think about for a minute. Suppose that a malware author wants to go change their executable. They need to change the callback domain. They could recompile the executable, but they may not. All right, what they may do instead is, and even if they do recompile the executable, right, recompiling it is likely not going to change the text section, right? What's going to change though is the data section, and so then I would have multiple samples. Let's say it's just the callback domain. That's a piece of data as opposed to a piece of code, right? The code does something with the callback domain. None of the code is changed though. Provided I use the same compiler settings, I'll likely have that same hash. Also, it's very common that attackers won't recompile at all. They'll simply basically hand jam or use binary patching to go binary patch that callback domain, changing the callback domain, and then we roll forward, right? So okay. What about that? What about that text value, the data value? Again, it's very likely that would have a different. Very likely that would have a different section hash. Mind you, changing anything in the file changes the overall hash of the file, right? And of course, we can see that up here. The hashes are calculated out here. Of course, MD5, SHA-1, SHA-256. But it's a very common thing that on the sections to only have section hashes in MD5 because a collision here is so ridiculously unlikely, and again, not really used from a security perspective. But what I can do then is track and say, okay, even though the hash of the file overall is different, that because the .text section has the same hash, or text sections have the same hashes, that these are likely share a common lineage or a common source code base. All right, and then final thing that I'll mention here is resources. All right, so I come into resources. There's only one resource, and in fact, you can even see the first few bytes over here. Neat, right? Notice here it shows the first few bytes in text. Okay, cool. By the way, if you wanted to get rid of that resource, or I say get rid of, excuse me, if you wanted to see what that resource actually is and inspect that using a hex editor or whatever, you can just say dump raw and save it out to disk. Okay. Now, I want to show you one other tool here with that sample1.exe, and that's going to be Cff Explorer. That's the one that looks like a little chili pepper. Now, these are free tools to download. Obviously, you'll have to download these and put these on a VM. Now, we're not executing the malware yet, so this is kind of safe-ish. Sometimes CFF's a little bit weird with opening. Let's give this one more shot here, and we'll drop this onto the desktop. Grab sample one. Okay, cool. Don't know what's up with CFF today, but rock on. Of course, demo fail for the win, or demos for the win. Okay, so we got CFF Explorer. It's running sample one here, it's loaded sample one. The thing that I really wanted to highlight here, the thing I wanted to show you that I'm a big fan of here is the resource editor. All right, so the resource editor here doesn't really do anything snappy that our resources section in basically in PE Studio does. But notice here, like, we've got some information that CFF Explorer doesn't provide us. When I come over here with the resource editor, I've got a hex dump or a string dump, like an entire string or hex dump. And so if this is arbitrary binary data, and there may be more files in the basically in the resources, again, we'd have all that here, right? So I'm a big fan of CFF Explorer for that. I don't have to dump it and then move over into a hex editor. It's just all right here for me, right? So I'm going to go ahead and close out sample one. We've taken a look at that, and I'm going to drop sample two in. Actually, which one was the one that I want to make sure that I'm grabbing there? Yeah, let's grab sample 2. Okay, sample 2 is a winner, right? So I thought it was sample 2 that was my winner. I mean, they're all winners, right? But again, like I said, I'll provide you a download link for these if you so desire. I say we'll provide you; it'll be there for you to download. And of course, it's running through PE Studio. Let's also go ahead and drop this into CFF Explorer as it rolls. Let's see, survey says, "Come on, CFF Explorer." Come on, baby. Oh, no. It's going to be cantankerous again. Surprise, right? Okay, cool. We'll open up here. And let's take a look at nothing in the resources, right? So if I don't have anything over in resources, nothing, right? Now, again, I'll say that Cff Explorer does a great job of pulling out some of the data. You'll notice here, like the timestamp, right? It shows it as a D-word value and doesn't convert it, right? Is that useful? Meh. I don't know. I mean, it shows it over here. It does actually, does it show the compile time? I take that back. It doesn't. I thought it was in here somewhere. Alas, bottom line, different tool, different way to display data. Call it for whatever it's worth. Notice here there's a section called .x, right? Well, that's a weird section name. Although, you know, what does weird even mean, right? We had one that we saw file we saw a while back where it was cursing Brian Krebs, right? So like the actual section names were something like F Brian Krebs. I can't remember. It was some vulgarity there. I think they talked about his mom a little bit too, and meh. Anyway, so I know there's not a lot of love for Krebs out there, but whatever. Don't talk bad about Krebs' mom, right? Anywho, so what about this, right? Well, virus total hits, yeah, says it's malicious. Don't take that always, because a lot of those, I'll mention that a lot of the engines, the antivirus engines, pivot off of one another. Meaning, if antivirus engine number 1 says something's bad, then AV engines 2, 3, and 4 looking like, well, AV engine 1 says it was bad, therefore it's bad. Right? It's like time out. That may not be a good assertion there. It may be that we want to go ahead and follow up on that ourselves, rather than just trusting virus total. Now, I'm not saying don't trust virus total. I'm just saying think for yourself and be aware that a high percentage there may just be an example of groupthink, right? And very frequently is, right? So for whatever that's worth, just bear that in mind as you proceed with your analysis. Okay, so let's take a look at our imports here, and then we'll drop into the debugger and take a look there. Now, you don't see a whole lot of imports here. We see a few here from some networking, some heap alloc, heap free, whatever. Take a look at strings. All right, let's see what we've got over here. Host name, password, something. Here's some program files, typed URLs. I love this, right? So it turns out here that with typed URLs, there's actually a registry key there where you can see what is somebody typed in versus, and if you paste a URL, and that's considered typed URL as well for Internet Explorer, this looks to me like an info stealer, right? I see a lot of stuff here around grabbing profiles, and let's take a look at some of this and see how this tool works, right? See if we can find some interesting portions around the basically around the tool, right? So let's see. We see some other. Let's see, here's a create file, a write file. Now, you don't see this in imports, by the way. If we come over to imports, you don't see create and write file. This thing is, I don't want to call it packed necessarily, but it does some runtime loading of imports, right? And we see those in the strings here, right? So we might, for instance, sort here by string name. You know, once you've done a little bit of this work, you'll start to see the import or be familiar with what is and isn't an import name. But let's say that I come up here to create, because create's a pretty common tool or common name. So I'm looking here at create file. Well, that I said common, right? Could be reg create key would be another one to go look for. Create file. I was thinking create process potentially. I didn't see that. Let's see. Here's get proc address. This is actually going to help us resolve some of these APIs at runtime. Okay. So what are we going to do now, right? Well, I've got some idea about this thing being an info stealer. Looking at email address, we saw the saw some of the registry functions there. Let's go ahead now and drop this bad boy into, first off, is the X32 or X64? Is it 32-bit? Okay, cool. I'm going to go ahead and take this, and I'm going to drag and drop him into X32 debug. And this is the spot where, at this point, you darn sure better have a snapshot, because the delta between what we were doing a second ago and what we're doing now is we're running the malware, right? So the fact that we are in a debugger means that the malware is executing. This is the spot where, if this is on your host machine, stop now, stop now, stop now. By the way, if you're thinking like, hey, Jake wouldn't give us live malware, wrong. Jake did give you live malware. It is, you are 100% responsible. I am not responsible, all that stuff, right? Okay, all right, so what do we have going on here, all right? Well, first off, if you've never been in a debugger, I want to call out a few things here. And again, remember, this is supposed to be super basic intro to malware. If you've been in a debugger before, this is probably nothing new to you. And in fact, if you've done lots of malware before, you probably shouldn't be attending this, because yes, this is super basic. Anyway, that said, let's get in and kind of walk through kind of what we're seeing here. Right now, I want you to notice down here, if you follow my cursor down here in the bottom left, you see the word paused. That is because we are indeed paused. That means we're not running any of the malware. But the second you drop this thing into a debugger, you have your malware into a debugger. Understand that there exists the possibility that the malware evades the debugger in some novel fashion that causes, let's call it catastrophic failure, right? So catastrophic failure meaning that it executes without us, and I say executes without our permission, and anything executing, of course, without our permission that continues to go execute, that is a huge bag of fail, right? So I never trust that, and in fact, we've seen practical attacks on debuggers where execution begins before we intended it. So again, this should be on your virtual machine. If it's not, bail now. Okay, we're in our CPU tab. Notice up here on the top of the tabs here with X32 debug that I have CPU tab. This is where we're going to start out, and we have multiple different panels inside of, or windows inside of our CPU tab. I call these panes generally. That's something that's been that's kind of worked for me. I'm going to start up here in my disassembly pane. This is in the top left, and this over here in this far left, this is control flow. You'll notice some dashed arrows over here, or dashed lines. These show jumps. Notice here the JLE, jump if less than or equal. And then the second panel over, or sorry, second column over here, these are the memory addresses, right? So the virtual memory addresses of a particular instruction. As we move over, another one to the another column to the right, we have the opcodes. Now, the reality here is that disassembly, and that's what you're really looking at here, is disassembly. Disassembly is a one-for-one translation between the binary opcode and this common language, or English language, if you want to call it, assembly code here. It's a one-for-one, basically a one-for-one translation, right? The only reason you would need this is if you wanted to go create different or binary patch and do something. There's even easier ways to do that. And I'll just mention that this is a column that I go ahead and I drag over here and I get rid of, because I value my screen space. I don't need it that much, right? But before I do that, I do want to highlight here that the x86 and certainly X64 instruction set is a variable length instruction set, right? And when I say variable length, what do I mean by that? What I mean is that these instructions each have a different length. I say each have a different length. Maybe a different length. You know, some of these are 1 byte instructions, some of these push instructions are single byte, and some of these other instructions are 5 bytes. Do I have any 6 byte instructions? I don't see any 6 bytes here. But you know, I think the longest one I've seen in x86 is like a 13 byte floating point instruction. There's some other weird ones that I've seen in x64, but they go up to be pretty humongous. Your average here, generally somewhere in that 1 to 6 bytes is usually what you see on average. Here's a, you know, here for instance is an example of a 6 byte instruction, right? Okay, so again, I don't really care too much about the opcodes because yes, I have a few of them memorized, but there's no reason to, honestly, other than just seeing them a lot. And so, and also, I'm not Neo. I don't see the matrix, right? I can read this, right? This disassembly. I can't always simply look at a bunch of opcodes and be like, oh, let me follow that code, right? There are some absolute rain men out there that can do it. It's not me. Okay, so next tab over here, or next column over, we have the actual assembly instructions, right? Now, how much assembly do you need to know? The answer is the more you know, the better at this you're going to be. There's just no question about this. But I'll also mention that I routinely teach people to do basic level analysis with very little, if any, assembly experience, right? So what does that say? You know, how do we do that, right? With very little to no assembly experience, and the answer is that basically we simply don't worry about what the assembly is saying. We focus on API calls, right? All the imports that we're talking about before, those are APIs. I'm going to show you how to go take a hard look at those. So notice here again, we've got a lot of these instructions. I don't have time to walk you through this. Normally when I teach malware at Rendition, we run a 5-day course, and a solid day of that is like deep dive into assembly. Now obviously we then continue to reinforce that throughout the course, learning how to reverse. Again, you know, I'm looking at my timer here and it looks like I've got about somewhere in that 45 minutes to an hour left on the clock. And so here we sit, right? So let's be real. I'm not going to get into the assembly, right? Okay. But we will highlight again that the more of this you know, the better off you are. Now, I'm sure that there's one or two folks on gatekeeping, generally folks here that are, you can't do malware reversing without assembly. And look, I'll be the first to tell you, you can't do the best malware analysis without knowing some assembly. But you can get targeted findings without knowing assembly, right? And that's what I want to show you today. Okay, this next column over here, the one that I'm moving the mouse through here, this is moving the cursor through. These are details, right? So basically, it's trying to say, hey, I recognize this is what these details are. So for instance, here it says push ESI. It says, hey, ESI points right now to the entry point, right? The entry point being the first instruction to be executed, that address. Now, by the time we get here, it may point somewhere else. So bear in mind here that these may dynamically update as we progress in the code, right? So just be aware of that here, right? That you may look and you're like, oh, okay, as we scroll down here, right? You're like, oh, okay, well, it's messing with the entry point here. Well, no, what's happening is the EIP, the instruction pointer, right? So the instruction pointer at this time, right, has these values. In X32 and X64 debugger are dynamically updating these details over. By the time we get here, by the time the instruction pointer is here, right, by the time we're executing here, we haven't executed anything yet other than the loader. By the time we execute to here, we may end up in basically ESI is going to point somewhere else. So just be aware of that. It's not a false positive. It's just a matter of know your tools, know what they're actually telling you, right? A lot of people are like, it generates a bunch of junk, and I'm like, no, it's not generating junk. It's just a matter of understanding what is the tool trying to tell you in the first place. Okay, this next, I'm going to move to the right over here, and these are our registers, right? Registers, I like to think about these as just buckets. You may remember a little logic puzzle, and if you don't remember this, by the way, go look this up. It's pretty cute. Basically, there's a man who has a canoe, and he has a bag of grain, a hen, and a fox. And his goal is to move these across the river, and he can only carry one of them in the canoe. He needs to move these all three across the river, but he can't leave the grain with can't leave the grain with the hen, and can't leave the hen with the fox, right? Or the hen will eat the grain, or the fox will eat the hen. Well, in order to do this, we really have this canoe with like one bucket. We have a temporary storage location, and we have to be very tactical about how we shift data in and out of that one spot. Well, that's very much like what we're dealing with here, except we have more than one spot. Right? What we have here now, of course, are multiple spots, each one of these registers being a spot, if you will. These registers here, EAX down through EDI. Now, EIP is special, eFlags is special. Flags basically control or log the output of instructions or the results of computations. But the rest of these here are just buckets, right? So what the compiler is doing, and ultimately then happens at runtime, the compiler is saying, okay, you've given me a bunch of code, and I know that I have to take this high-level code and I have to output this in a way that can be executed on the processor that only has 8 buckets. And what I'm going to have to do is I'm going to have to create a logic puzzle or solve a logic puzzle that only allows me to execute and store X number of these, in this case 8 at a time. Now, as we move into X64 processors running in X64 mode, this of course is an X64 processor running in 32-bit mode, or 32-bit emulation of. But the X64 processors, they have an additional 8 general purpose registers, R8 through R15. So again, it makes the logic puzzle a little easier. So move down here, where my cursor is highlighting below the registers. Actually, before I move on, let me mention here that you can double click on a register. You're on God mode in a debugger, and you can modify the values all day long. Right now, this is all the same value interpreted different ways, but if I wanted to make this 0, I can do that. All right, now I'm going to cancel this because I'm going to break anything, but you can change. You're in God mode. You can change anything you want here. Go, go, go. Down here, we have the function arguments, right? So this is the next piece here. Now, we're not calling a function, so right now this has no meaning. But what we're looking at here is effectively interpreting, at the time of a function call, what arguments are being passed to the function, right? So So that's something to look at there as well. I'll take a look at that as we get into a function call, and then I'll have a little more meaning. Down here let's come over here next. As we move over, this is our details or hints pane. The details pane here shows us indeed, notice here it says push EBP. Well, because EBP, the EBP register, is being placed onto the stack, which we'll talk about in just a minute. Because it's being placed onto the stack, it shows us the actual value of EBP currently, right? So it's like, oh, hey, so you don't have to go cross-reference and go look it up here. Now, this one's pretty easy, so I may not have needed this, but when it's dereferencing something elsewhere in memory, I don't have to like change my dump location and go jump there and read it, and this handles that for me, right? And so I like that. Down here, beneath that, we have our dump panes, right? And our dump pane basically is just a hex dump of a random area, I say random, of an area in memory, all right? In this particular case, I think it's sitting in NTDLL, but any memory location that I want to go to, I can simply Control-G, and I can say, hey, go over to this memory location, all right? So if I wanted to go to, let's say, 413, I don't know, 800, right? We can simply jump there and we can see the actual data here. Now, this doesn't make a whole lot of sense right now because, well, I just jumped somewhere randomly, but you can see indeed that we can go see both the hex values as well as the ASCII values. And if you right click inside here, you can see then that maybe, for instance, let's say that you wanted to go in and change these to addresses, right? Let's say that you're looking at, let's say you're looking at unsigned, right? Let me convert these into addresses, or maybe hex addresses is a better plan there. Go integer. And we'll just say hex long, right? So this takes care of all the little endianness for us. Again, it's all the same data, just looking at a different way to interpret it. I typically have it on hex ASCII. Notice here, though, again, right? If you're familiar with little endian, you know, the most significant versus least significant byte. Notice here, F9 40006A, right? So if I drop back over here and I say, hey, make these addresses. Notice here that it's flipped. Right, so it's actually gone through and flipped the addresses for us, right? Done a little endian, right? So again, 6A0040F9. And if you're not familiar with that, don't worry about it. Little endianness for the win. Google that down the road. And then finally, over here on the right side, we have our stack. The stack is tracked by ESP. ESP stands for the extended stack pointer, right? It's the SP stack pointer. The stack is a temporary scratch space, a temporary storage or scratch space for the processor, right? And the stack stores very temporary data that we might need, and it's a last in first out buffer, right? So push places something on the stack. A pop removes something from the stack, right? So typically, if we mentioned before here that we have a fixed number of buckets, if we need to go save a piece of data for immediate reuse or reuse in the very short term, we're going to put it on the stack. Local variables. If you're a programmer and you remember local versus global variables go on the stack, and global variables go elsewhere in memory, typically on a heap, right? Something to mention there. Okay, a couple of things I want to highlight here before we get, or as we get going, right? I'm going to go right click here, and one of my go-to functions here in the basically in the malware, in the debugger is when analyzing malware is I'm going to say let's go ahead and search for, and I want to say current modular, and I say then show me intermodular calls, right? So what are we doing here, right? Well, everything interesting in malware happens via an API, Windows API. And in fact, we're looking at some API names, some interesting API names. And what I'm interested in knowing here is what calls are happening that go outside of this, basically outside of this malware, right? And so I'm going to right click here, and you'll see then some of these calls. Now, this one's an interesting piece of malware because, of course, it has some obfuscation where we can see the names of APIs. We don't see them directly imported. I'm going to drag, this is currently sample 2, I'm going to drag sample 1 in because it doesn't have as much of that, and we're going to drop that into X32 debug so that I can show you another example of this, right? Okay, so here's X32 debug with sample 1, and I'm going to right click over here and say, hey, inside the current module, show me intermodular calls to another module, like to a DLL, right? Again, my goal here is to try to identify how particular portions of an API how malware is using certain portions of this API. All right, so now that I've got a bunch of these, I could say, for instance, come down here into the search bar, and I could say, hey, show me anything that contains the word create. All right, so create process. Well, I'm interested in that. Right? Why are the two create processes? Create process A and W. Well, one of these uses an ASCII argument, the other one uses a Unicode argument. Why are they both on the same piece of malware? Maybe they're sharing code. Maybe somebody wrote one piece, somebody wrote another. I don't know. But I can go double click on this and I can say, hey, let's go take a look around create process. Right? So I'm going to adjust my windows here a little bit to get some better, a little bit better feel. And here's create process. Right? So let's take a look. Create process A. What's going on here? Well, that first argument to create process, and by the way, if you're not familiar with this, we can simply go to the Googles. Oops. Why did I open Internet Explorer? What a horrible, horrible plan. Don't do that, right? Okay, so let's try this instead, and we'll use Firefox, and I'm going to say create process. And you can use the A or you can leave the A off. I don't really care. This is an entirely up to you kind of thing, right? Okay, so if you leave the A off, it's still going to get you to the create process function. That's the reality. And I just go over to the Microsoft documentation. It's funny because people gripe all the time about how bad the Microsoft documentation is. Honestly, it's really not that bad. People, yeah, I actually think it's pretty good. What I will mention is, a lot of these folks that gripe about Microsoft's documentation, they're big open source buffs, right? And they're like, well, I can't go read the source. I'm like, well, you can't, but wow, they give you a lot of stuff here, right? So I notice here the application name and the command line, those are parameters 1 and 2. And as I look back at these pushes, that's really what I'm looking at here, right? So EAX and ECX, what's loaded in those, right? Well, look over here, ECX, we have a, let's see, that gets XORed with itself, right? XORing anything with itself sets it to 0, so the command line isn't used, and in which case, right, if we read the documentation, the RTFM, right, read the fine manual, we would see then that the application name can be null, right? But if it is null, then the command line string can't be null. Well, we already know the command line string is null, right? And I say we know this because, right, I'm looking here and I'm backing up from the call, right? So anytime, and again, this is going to get deep into assembly. I mentioned before, I don't have time to get into all the reasons for and all the, all the pieces around assembly here. But what I will say is that here we're going to back up pushes from a call. So this is argument 1, argument 2, 3, or if you count from 0, whatever. I'm not going to get into that debate here. It's the first argument, second argument, third, fourth, etc. Right? Okay, so to come back here, like I said, I'm trying to find out what the process name is. I have command line, I have application name, right? So both of those can't be null when I read the fine manual. I know that anything XORed with itself is 0, meaning null. So I know that the command line is null, hence the application name can't be. So now I'm literally just going to back up and say, hey, where did EAX last get set, right? Now, before I do this, or as I do this, let's go ahead then and take a look at IDA Pro, yet another tool that we can use. IDA Pro is obscenely expensive, well worth the money if you're doing a lot of this work though. We're just going to drop into the freeware version and take a quick look. Freeware is not licensed for commercial use. This, of course, is not commercial use, and my regular malware VM has all that, has the license and all that. Anyway, I want to show you in the same version you're going to use, and so what I want to drop back, or the same version that you might use. And so I'm just going to drop back here and give you an example of taking a look at that create process A and how much easier it makes it here. By the way, I'm going to go and change my font just to make it just a little bit bigger here. And I need to drop back over to IDA view, and then options font comes up. And sadly with IDA, it only allows you to go change the font in the big window, the assembly window, but that's fine. It's still good for us. But as I come over here to my imports window, everything's still the same, right? And so I'm going to control F over here, and I'm going to say, hey, show me create process. All right, so create. I'll need to spell create correctly, as it turns out. So I'm going to go grab this create process. Create process A, I believe, is what we're looking at. And then I'm going to use an X to cross-reference. I'm going to say, hey, show me my cross-references. Where is this thing referenced from? And this is very much like, this is a two-step process that basically got us the same data, or gets us to the same place, that basically the search for intermodular calls got us, right? This gets us to the same spot, right? So I click OK over here. One of the things I like about IDA that's super useful is I simply press here and I highlight EAX. and then you can see, okay, I highlight EAX, and game on. We are we're go here, right? Okay, so notice here then it shows the highlights of what happened to EAX before this. Well, I see this being moved into an offset with a structure right before a call. I also see a push, which is very frequently a push, sending an argument to a basically sending an argument to a function. Let's see some other pushes here, right? So we see the push, and it says ComSpec, right? Well, what is ComSpec? Well, let's Google ComSpec if we're not familiar with it, or yeah, let's Google ComSpec. We'll do that. I don't want to use any dirty knowledge here, all right? So ComSpec. While we're doing that, I'm going to go ahead and I'm going to come over into a set. What I meant was a set, and I'm going to take a look at my variables, and you'll notice here there's a ComSpec. Oh. Notice here there's a ComSpec, and it is the command prompt, right? ComSpec is the environment variable in DOS, Windows, etc. Points to the command line interpreter. Why might you use the word ComSpec here, right? So, well, the answer is that if I simply expand my environment strings first, right? And I suspect if we drop into this call here, we will see a, maybe not. I was going to say an expand environment strings. We'll see. Was expecting to see that here. Basically, typically what we're going to expect to see is that ComSpec is going to basically be resolved to the command prompt, right? Okay, so again, we're not executing IDA-Pro, but I just wanted to highlight kind of some thoughts around that. I'm going to go ahead now and let's go ahead and set in my, let's say my sample one. This is the one we were looking at with create process A. I'm going to go ahead now and set a breakpoint here, right? So F2, set a breakpoint. I'm also going to drop back over here in my References tab. This is where the, remember when I said, hey, let's go try to find intermodular calls? This is where they all went, right? We'll create processes. Do I want to know when a process gets created? Oh, heck yes, right? So I'm going to press F2 and set a breakpoint there as well. Then I'm going to delete this, and I'm going to take a look at some of my other intermodular calls. Anything else that I'm interested in here, right? And the answer is, yeah, I bet there probably is. Let's see. I'm just kind of scroll around here a little bit. What else do I see? It might be, I mean, there's all kinds of stuff here that might be interesting, right? But, like, what is the most interesting? Let's see. Lots of stuff going here. How about I look at it right? Yeah, let's do this, right? So, actually, is there a create? Yeah, so let's do this. We'll go ahead. This is our process list. Basically, we're walking a process list. Let's see your tool help. No. Okay, so that process 32 first and next, if you Google that, it's going to then basically look at the return from a from a call called create tool help 32 snapshot, right? And again, if you just read the manual on this, if you Google process 32 first or next, you would see this create tool help 32 snapshot. Create tool help 32 snapshot. Right? Isn't it cool that Google just auto-completed and they were like, malware? Did you mean how is it used in malware? Of course it is, right? Okay, so what I'm going to do here then is I'm going to say set bpx, right? What I'm saying here is set a breakpoint, and this is going to be on kernel 32 dot create tool help 32 snapshot. And it says, fail. It wants the set bpx kernel 32. So notice there that there are very few things in Windows that are case sensitive, and it turns out that certainly in the debugger here, it actually is case sensitive. So okay, cool. Create tool help 32 snapshot with the proper camel case got us there. In fact, you'll note here, indeed the camel case, I had it all lowercase like a lazy bum, and indeed not so much, right? So now we have a breakpoint there, and in fact we can view all of our breakpoints here. You'll notice that several of these are set in the malware, whereas one of these is actually set not in the malware, it's set in the DLL itself, right? Now, the reason I did that here is that I don't see a call to this, right? But I know that because there's a process 32 first, and again, this is a lot of experience that goes into this, and reading. You don't have to be a dev to reverse engineer malware, but the more developer documentation you read and understand, the better you're going to be at reversing malware, because you're going to understand how these APIs are used, right? And you can't do interesting stuff in Windows without calling APIs. The system calls, do all the interesting stuff for us. So I'm going to go ahead now and run the malware. Now, I don't know what's going to happen here, right? And so I'm going to go ahead and take a snapshot, and I'm going to say pre-exec. All right, so pre-execution. The reason I do this is I can jump back to this point and I can go play with this. Maybe I wanted to set some other breakpoints and I just wasn't sure about those yet. So I'm going to go run now, and basically this is going to run the malware in a controlled environment so that I can inspect how these APIs are being used. This is the stuff we can't do with a sandbox, right? First off, I want to see, do these ever get hit, and then secondarily, like if they do get hit, how are they being used, right? And again, this lets us be a little bit more surgical. So I'm going to go ahead then and run, or press F9, right? So you can do a debug, run, F9 is the hotkey, F2 is the hotkey to go set a breakpoint. I'm going to go ahead and run, and we're running. Survey says, okay. Sometimes, by the way, I'm going to throw this out here. Sometimes you run you run malware, and it just does its thing, and we don't get a pause, right? This is one of the great reasons that we have a snapshot, right? So I may hop over to sample 2 here because that's more fun. Also, I believe this does some injection. I just saw my screen flash there, which is never a good thing. I know it does some hooking. I remember that. But I don't see the call to create 1232 snapshot would be a prerequisite to hooking, typically. Although there's another call, there are other calls like NT query system information that could also be used. We took a guess here. We may not get a win. I grabbed some samples here that I remember being fun, but I couldn't, right off the bat, wasn't pulling reports for those. So you're watching a live, I don't want to say a live debug fail, a live demo fail. What I'm going to do here, I'm going to snapshot revert. All right, so let's do this. We'll drop back to pre-exec. We're not going to run this. We'll drop in a sample 2 because. Right. Come on, slowness. Okay, so as this restores, we'll drop in a sample 2 and take a look at that in the debugger. Again, sample 1, there's certainly, you may let this run longer and get there. I don't want to be in a position where it's sleeping to avoid analysis or something along those lines. By the way, if you think that's happening, one of the things you can do here is set BPX. I just said I wasn't going to do anything else with this, but I am now. Set BPX, kernel 32. BPX, kernel 32.sleep with a capital S. That is one of the most maddening things for me there. That, okay, let's go run. Oh, cancel. And CPU and run. So here we go. Okay, so we're sleeping, right? Okay, so let's see. That's a jump to sleep. What's the argument that's being passed? It looks like it's sleeping a very, very, very short time here. It looks like sleeping, and the way I say very short time, these are milliseconds. Sometimes this is used in anti-debug. All right, so sleep only takes one argument. I'm going to F8 and single step into the sleep call. And again, you can see here in the basically the single argument on the stack. This is where the function arguments become interesting. It just slept for 1 millisecond, right? I'm going to say debug and execute until user code, right? Or run till user code. And here we see then the basically the call. ESI currently holds the value of sleep. And by the way, how interesting, the EDI holds the value hello, or a pointer to hello world. That doesn't seem, or say it doesn't seem. It seems interesting to me, but hey, whatever, right? Okay, so we're going to then take an unconditional jump, and we're going to jump back up here until we call ESI, which is also our, let's see, a sleep, right? So EBX, and then call ESI. So push EBX. EBX is 1 millisecond. Okay, so what are we doing here? We are thrashing and entering an infinite loop, all right? So that's what we're looking at here. How do we get here, all right? What I suspect has happened is, by the way, since it says this whole hello world thing, I don't know for sure what's happening without backing up here. And I'm beginning to think, like, what did they do here that was I think they detect the debugging. I don't have anti-debugging features on the debugger, meaning like the hide my debugger features. I don't have those enabled here because I wanted to have a clean debugger to walk through some of this with. But it looks like, and again, this is a great example of something detecting its analysis environment, because what you have here effectively, and I think I'm pretty sure that's what's happening here. We'll drop into another sample to sample 2 to play with that. That was the one I'd intended to play with the most anyway, but alas here, great example of us basically in an infinite loop where we're just going to sleep, right? So we could wait forever, and short of another thread breaking away, this thing is just going to go run, constantly calling the sleep API. Now, why call the sleep API with a 1 millisecond every time? The answer is that we routinely see our sandboxes looking for the number of APIs that are being called. Also, calls for very long sleeps may set off some kind of what am I looking for here? A kind of a heuristic detection. So another thing that worth noting here is there may have been a timer set basically to interrupt. Basically some other kernel event or kernel timer. I say a kernel event or an event or timer set basically to exit this code. So it may sleep for some period of time before that event fires and breaks it out of this loop. Again, I don't have time for all that. It's supposed to be basic, and I feel like I'm getting this example. These examples are supposed to be basic. I pulled one here that may be out of our depth for what we're trying to do. But hopefully you now have some more experience with the debugger, and you're seeing me work through kind of I don't call it an interesting problem, but a problem nonetheless. I'm going to go and close this out and let that be. Let's hop back over now to the other X32 debug. This is our our other X32 debug. And what I want to do here is I want to take a look back with sample 2 and take a look at our strings, right? And we have a lot of strings that themselves are apparently API names. I'm going to go ahead and go back to the blacklisted strings, right? Just to highlight those very quickly here. And as we go to blacklisted strings, it helps to know that some of these, that some of these actually are API names. Let's see, some of these, like for instance, these ZW allocate virtual memory, ZW query information process, read virtual memory, resume thread, etc. These are all API names, right? So seeing these is certainly helpful to know. I also see a lot of things here that look like directory lists, a find first file, as well as certainly things that look like registry keys. And those registry keys, I would expect to be certainly being queried. And let's see if we have any of the reg calls in the R's. Reg calls, R's, reg. We don't, right? Okay, so what am I going to do? Well, I think with this one, I'm actually going to go ahead and set, and you see some other registry keys and all that. I'm going to go ahead here. No. Tried to go away on us there. Let's not do that. Oh, I see what's happening here. I tried to drop in VMware, try to take over my minimize there, right? Okay, so what I'm going to do here is I'm going to go ahead and set BPX. And it happens to be at VAPI32, right? So at VAPI, and I'm going to say reg open key A. And we're going to copy that because we're going to use it again here in just a second. Reg open key VAPI32. Sorry, that's what I'm invalid address. Reg open key. It's going to be one of those days. I can see it now. Set VPX. So what we're going to do, let's go over to our symbols, and we'll go to, is the VAPI32 loaded? Okay, so that'll do it. So VAPI32 isn't loaded yet. That is a great reason why we can't set a breakpoint there. Okay, so what I'm going to do here is I'm going to change over here my preferences, and I'm going to say, hey, I want you to break anytime you do a DLL load. This is probably a good thing since we are going to dynamically resolve some of our APIs. I'm going to go ahead now and run. So I'm going to press F9 here, and debugging stopped. Man, this may be a giant fail here for the samples that I picked out. Let's go ahead and revert to snapshot. This is why you always have snapshots running, or snapshots of your stuff. Also, probably should have grabbed or run through some samples here. I grabbed a couple of samples that I remember being fun. I thought that they were fairly easy, and of course, I may be shooting myself in the foot here. All of these are ones that we reversed in the past. I just, as a, like, yeah, I'm trying to keep this as relatively simple as possible. So I'm going to drop into plugins, and there's Silahide. Let's see, what do I have set in Silahide? Nothing. Okay, so yeah, loaded. Let's go ahead then, and I'm going to drop in basically the basic runs. The idea here with Silahide is that it allows you to go in and hide from your debuggers. Right? You'll notice here that like you have different profiles set up, and VM Protect and Themida check for different things, and generally all this stuff. A lot of folks are like, let me check all the boxes. The problem is every one of these boxes that you check is modifying how the operating system works, and the underlying OS works, and so you don't want to check stuff that you don't necessarily need. Right? So that obviously can be anything that you check that's modifying the OS. Can obviously cause problems if basically I want to use the minimum number of selections that I can to go hide my debugger. Right? Okay. Notice it'll say here whether it's necessary to restart the program or not. It says in this case, based on what we're selecting, it's not necessary. Right? So what I'm going to do here again is I'm going to come back to options and preferences, and I'm going to ask it then to go ahead and break on a DLL load. I'm also going to ask it to go ahead, now that I'm thinking about it, we're going to go ahead and break on start of a new thread. All right? So I'm going to go ahead and run. Okay, notice down here it says, hey, there's a thread started and the entries in NTDLL. Not really interested for the moment there. Let's run again, and debugging stopped. Okay, I'm going to go ahead now and bail on this sample. We're going to sample 3, right? And I hate to be that guy, but I've got, it looks like about 20-ish minutes left, 25 minutes left. I'm going to drop back here to one that is to a sample, or a space where we've got a clean setup. Let's drop into sample 3 and we'll roll there. I really wanted to give you some targeted findings, right, that were easy to run through without having to explain a whole lot. Bear in mind here, I'll mention that there's a lot of iterative here where I'll kick something into a debugger, get some targeted findings, rinse, lather, repeat. Obviously, it's detecting my debugger somewhere there. I'm not detecting my debugger or my virtual machine. I can't remember what we did with that sample. And just again, for the sake of time here, let me drop and grab sample 3 here, and we will put this into our debugger. Drop that X32 debug. We haven't done anything with this one yet, so game on, and hopefully we get lucky with some easy, because I would normally do metadata analysis, right? So static properties analysis. I don't have time to run back through that here. We're going to start with search for current module, intermodular calls. Again, I remember this one being interesting, or we wouldn't have it here. Let's see. Let's go for creates. Create mutex for the win. Okay, so we're going to go ahead and set F2, F2, F2. Okay, so I'm going to go ahead and set breakpoints here using the F2 key. I'm setting these on basically 3 of these. I'm going to go ahead and take another snapshot, and let's take a new one here, pre-exec2. Because now I can just drop right back to this. This hopefully should give us some targeted findings. Very quickly, I want to talk about mutexes. Mutex is a mutual exclusion. And a mutual exclusion allows us, allows us to create a tool or a tool mark that's only visible in memory, right? Only visible in memory. And so when I take that the tool mark that's only visible in memory, this is a great IOC. Now, what malware uses this for is to prevent multiple reinfection. In fact, we saw this in WannaCry. So we produced a tool rendition called Tearstopper that basically used the mutex that WannaCry was using to know whether or not it was in the middle of encryption. And so by throwing that mutex, by planting that flag and creating that mutex before WannaCry got there, we were able on some of our very obscenely expensive lab machines that a couple of customers and other operational technology machines that they had concerns about patching, we were able to say, okay, look, this is our best bad plan, is to go create this mutex that WannaCry believes is it already there on the system, right? So that's a mutex, and we're always interested in that. Certainly any processes being created, and then any files. Create file means create or open a file. Let's also take a look at reg. Let's see, do we have any regs? No, nothing there. Let's see. That's not to say nothing's done with the registry. Please don't think that for a minute. It may simply be that the registry calls aren't explicitly imported, and maybe imported at runtime. Here's a write file. Let's actually take a look at writes as well. Lots of write files. All right, so let's see here. Let's have. Okay, and we'll use these and kind of run through some examples here. Okay, so I'm going to go ahead and run, and I may shake the chicken bones here and hope that we have a good successful run. And we run. We are now at the basically at, and it's called an int3 breakpoint. Let's hop back over to the CPU. int3, by the way, is a software breakpoint, right? And so we can now see that we are writing to a file. This is call dword write file, right? Okay, well, what file we're writing to? Well, I need to know what file we're writing to. And by the way, our arguments over here, you can see these arguments over here in the arguments pane. It would help to know what write file is. And again, we're just going to Google that, right, or what the arguments for write file are supposed to be. We're simply going to Google those. And when we do, we're able to see then that write file. Come on, slowness, all right? So the write file, its first argument is a handle, basically to the file to write. Now that handle here is handle 8C, all right? So I can hop over to handles. You notice here they're all empty, but if you right-click over here and say refresh, they show you the actual handle values, right, and what those handles are. And so handle 8C is the one that we were writing to, and now I'm like, okay, well, what is that? Well, it's device con drive, right? Well, now I'm going to have to go and look and say, what is device, and Google what is device con drive? Is it interesting? Con DRV is it interesting to us or not? In this case, I'm going to tell you that it's less interesting. We're going to keep right on rolling. But I now know what file is being written to. If you want to know how the rest of that's working, notice here the rest of the arguments here, right? So basically our buffer, and basically the buffer is the pointer. You scroll down here a little bit, it says, hey, this is a pointer to the buffer containing the data to be written. How much data we're writing, right? So basically the number of bytes to write. And then we have an output parameter, the number of bytes that were written. Because you may request 100 bytes to be written, but maybe only 50 actually get written, right? Okay, this one's not interesting. Let's continue. All right, so we're going to run again. Pause at the same breakpoint. By the way, nothing changed here, right? So 8C, all right? Is that interesting? I don't know yet. We think no. Condirv, not really interesting. If I run this a few times and I'm like, man, you know what, this one's really not interesting to me, I can do one of two things. I can go ahead and I can press F2 again and clear the breakpoint, right? Now, that takes it out completely. Alternatively, I can hop back over here and I can say, you know what, instead of clearing it, I may want to re-enable it. I press the space bar here and notice it changes to disabled, right? Because now I'm going to be able to go see another call to write file somewhere else. Now I'm set at a different breakpoint. Let's go examine that. Well, it's a call to write file. And notice again, it's 8C. Right? I'm going to go ahead and just clear this breakpoint. Let's see where we go next. We're running. Come on, give us some targeted analysis here, or some targeted findings, right? We've gone through a lot of how to use a debugger and some of the stuff to look for, but wow, would it be cool to have a sample that getting ready to do here is I'm getting ready to drop back to one of my oldies but goodies. Yeah, not pausing there at all. Okay, so we got lots of write files initially. Again, this may be that I just need to wait longer. I don't have that kind of time in this particular scenario, and you know, again, want to keep this fairly simple. So let's do this. We're going to drop back to a snapshot. I'm going to go grab a sample that we know works, and instead of grabbing grab one from our course. I grabbed some stuff that we had reversed recently for different reasons. I say recently, like in the last year, for different reasons, as opposed to just going into the stuff that's in the malware course that we teach. and I'm just going to grab one out of there. I don't want to say out of desperation, but that's about where we're at, because I got about 20 minutes, 20 minutes-ish left, and I want to get to a spot that we can. Let's see here. Let's jump over to C. Labs. DLL or executable. Executable for the win. Okay, cool. So let me do this. What I'm going to do, I'm just going to copy this. Let's call this mutex.exe. Okay. Okay. And fun. And it even has a neat icon. Right, so okay, let's go ahead then, and we'll drop this in X32 debug. Well, that's fun, of course, right? Of course. Let's see. I'm gonna grab. You can see things are just not going my way today. I should have grabbed, again, one that I know, or some stuff that I know 100% is not going to fail. I want that one. Let me. Let's grab one of these here. You notice I didn't change the name of the executable here, and it doesn't actually have an exe extension. Okay, cool. So this one, hopefully this is an easy win. Let's go find references, or sorry, search for current module, intermodular calls. Okay, more regs. Let's go ahead and set some breakpoints here around the reg create key, reg open. I'm going to go ahead and search for reg here just to get those those keys. Those APIs. I'm going to set some breakpoints around here. This one's interesting, reg notify change key value. This basically sets up a callback routine, so you don't have to check to see if something's been changed. This is, I don't want to say always used by malware, but very often used by malware. All right, so I'll set some breakpoints around here. You don't have to set them on all of these. Ordinarily, I would. Right? And by the way, too, you can go set these actually in the API itself rather than in the malware. There's advantages to doing each. One of the big advantages of setting in the API or in the DLL is that you don't have to deal with hitting F2 a bunch of times like this, right? So basically, you do it once, and that's it. Right? So references, H2, and we'll have 2 again, and F2. Sure, we'll delete value. Delete value and set value. Okay. So I got a bunch of these set, and then I'm also going to look to see was there a mutex in this. There is. We'll go ahead and whack F2 there, and let's go ahead and run. Okay. We are setting at a breakpoint. I'm going to hop back over to CPU. Notice it's create mutex A. Okay. Let's now come back. Good to go. Now we have some targeted findings. Wow. It's been one of those days, right? Okay. So, and again, like I said, it was one of those. I'm going to call mea culpa here and say that I wanted to go grab some brand new, I say brand new, stuff that we've done, but forgot, again, from a how beginner-friendly some of this was. And again, I'm on a short time period here to get you to a spot you got some targeted findings. So, targeted finding, right, create mutex, right? So, Microsoft Dreams is the name of the mutex. Is good, bad, or indifferent? Well, the deal here is that by creating this, the malware is able to go and see basically, is it already there? It's able to go plant a flag. Some malware, we can abuse the logic for it, or as well as some malware doesn't want to run if another particular malware sample that it may identify by mutex is also already running. Right? So we may be able there to basically to get some useful insight. I'll mention that if your EDR can't show mutexes, right? No problem. You have a tool from Microsoft sysinternals, or used to be just direct sysinternals. Now Microsoft owns sysinternals. But there's a tool from sysinternals called handle.exe, and you can download Handle and certainly use that to query handles on your machine. So sysinternals, what that's going for there. Garbage. Took a week and a half for Firefox to start. I've got a bunch running on this VM, sadly, and not enough memory, apparently. So let's do sysinternals. Sysinternals handle. So, okay. So the handle tool here, I'll just mention, I'm not going to go over there, but I'll mention that you can use this to go query mutexes. You can use other tools like Process Hacker, certainly to see mutexes as well. If I wanted to go look at a particular process here, and in my case here, I've got this weird, basically this weird sample. Let's see, which one do we have? This is our guy. Yeah, so basically, I take it back. So what we got here is that DLL loader. Basically what's happening here is, so we're looking at basically the copy of that executable. Okay, so that's of course running here. If we wanted to go take a look at the handles here, we can come over and notice here, access denied, because I need to be admin. Just double clicked on that, run as admin. I'm watching my time here. I got about 10-15 minutes left. Okay, so very quickly here, I just want to show you kind of that piece. So if I go take a look at handles here, you'll notice that we don't have any mutexes, or sometimes they're referred to as mutants here. I'm going to go ahead and inside my debugger. All right, so remember here we're broken on and haven't actually continued past this create mutex. All right, but now I'm going to press F8 and say, hey, I want to go ahead and execute this create mutex. And what I'm going to do is then I'm going to hop over to Process Hacker. Right? And you'll notice here that there's now a mutant, right? Now notice here the API call is mutex, but in the Microsoft internal documentation they call it a mutant, kind of like X-Men mutants, and you see here Microsoft Dreams. Now this is a hard thing for an attacker to change, right? Because the whole purpose of a mutex is to prevent multiple reinfection, or to plant a flag by a name saying, hey, I am here, so that other things can see that you're there. Configure did this very successfully, as do lots of other pieces of malware that want to randomize the name of the executable or DLL on the system. All right, so if you think about an executable or DLL on the system, if we wanted to randomize the name, I can't then go query the process list and say, am I running, right? I would see random executables running, but I wouldn't know maybe random executable names, but I couldn't tell for sure that it's me, right, without doing more analysis. Well, the mutex helps me with that. Now, if I find one of these, this means that it's very difficult for the attacker to change, because changing it will negates the functionality, right? Now, all of the old malware checking for the old mutex, right, before we change it, no longer works with the new malware that drops the new mutex. You see the problem here, right? So we generally want to look for things that are hard for the attackers to change. This is one of them. So I'm going to list Microsoft Dreams as an IOC for this particular malware, an indicator of compromise, right? And it's a fairly reliable one, right? Because, well, I mean, it's hard-coded into the malware. We see it being created here with create mutex. I'm going to go and log that as one of my go-tos, right? Go-to IOCs. I'm going to go ahead and run again. And now it says debugging stopped. Okay, well, so we got one targeted finding here without getting too deep into the debugger. Let's see, snapshot. I didn't take a snapshot before this one, right? So I'm going back to pre-exec 2. Blah. That's fine. We'll go grab another. I think it may have again detected my debugger. I'm not 100% sure. I didn't have debugger detection set up because or anti-detection set up because I wanted to kind of walk through some of that. But again, teaching something for days with a whole lesson plan versus teaching something over, basically doing a seminar over an hour and a half or 2 hours, kind of a different play there. And let's see. Let's go ahead then. I'm going to hop back over here to Labs, close Internet Explorer because it's a devil. And let's see. We're in Registry. Let's go and we'll grab this other one here, the 45K, and I'll drop that into the X32 debug. Let's see what that one says. We'll see if we can find another targeted or get some more targeted findings here. Again, I'll drop the samples that we've used up to this point in our I'll drop the samples we've used up to this point in basically in a zip file that you can download. And again, we're going to search for current module, intermodular calls. While I'm doing this, this is probably a great time to mention that we have barely scratched the surface, just barely scratched the surface here, right? You really need to do spend time with a debugger, even like on the debugger, right? You may notice that I'm doing kind of the same thing. It's not that I'm a one-trick pony, it's that I don't have time to go into like, hey, here's how to do a bunch of analysis that will get you to, I was trying to show you how to get some targeted findings. This is the way that I show a lot of my folks to go get some of these. But I see some resource-related API calls, so let's go and take a look at this in Cff Explorer. Come on, buddy. And I mentioned before, I really like Cff Explorer because of the resources, right? Let's see. Okay, so we do have a couple of resources here. One is named 102 and one is named 103 under the word file. All right, well, I don't recognize the code here. Like, I can't step back and be like, oh, I recognize that. That's obviously whatever. I don't know what that is. I don't see a file header there or an MZ header. Maybe I dump those out. Maybe I just look at how they're ultimately being used, right? Okay, so I wanted to see if there's any very easy to run with piece there. Let's take a look at what we've got here. First off, I'm going to go ahead and set some anti-debugging options since this is going to be our last ride. So sell a hide, and I'm going to go ahead and load. I'm going to do the basic. Cool. And let's do this. Let's do creates. Okay, so we definitely have some possibility for code injection. That's a ToolHub 32 snapshot walk on the process list. I'm going to take a look at services too, because it's got to create service. Why wouldn't I want to see that? Here's a reg create key. Nope, cancel. So F2. And I'm going to leave the create files out for a moment. But the reg create key seems interesting, and we'll look at the create ToolHub 32 snapshot and create service. Right. So I'm going to go ahead and run and see if we get a pause here. Here we go, pause. Okay, so we hit a breakpoint. Let's hop back over to the CPU pane and see which one it is. Here we've got a create service. Awesome. Okay, so this create service, right? You notice here that we have a number of different arguments. I'm down here on my stack window. Now I said before these are our arguments over here in the top right. So I say top right, excuse me, the middle right pane are function arguments, but realistically here, create service takes too many arguments to show all of them. In fact, we'll just do this one last internet search. I think this is going to be our last internet search together, but create service. And we'll take a look at the arguments there. You'll notice that there's only 5 arguments here. And in fact, you can change this, right? If you wanted to have more arguments here, right? Just typically that they aren't needed, right? So in this particular case, I think create service takes 9, but don't hold me to that. We'll see in just a second. But basically here what we're looking at are the arguments, and basically how do those play out together. More than 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so bad on me for that, right? Basically here, though, you see the arguments passed to, or the actual arguments would be passed to create service. So I'm looking here at the binary path name. Now look, you can see here, right, that the binary path name, there's only one thing on the stack that even matches that in this area here, right? But arguments 2 and 3 are the service name, right? So you're looking at the service name and display name. Those are 2 and 3, and then argument 8, the binary path name, right? So we count up, right? So we're looking at 1, 2, and 3, right? So FGSM is used, right? So 4, 5, 6, 7, 8 then is our binary path, right? So FGSM.sys. This is probably something I want to go take a look at, right? So that's my syswow64. Let's do this. dir. System32 drivers, system32 fgsm.sys, right? It says not found. Well, what's going on here, right? Well, remember this is a 32-bit malware sample. We're an X32 debug, right? So what I need to do is I need to go take a look at syswow64, right? Remember I talked about the file system redirection earlier. That's what you're looking at here, right? So fgsm.sys, right? and now you see indeed FGSM.sys. Now, obviously, then this malware dropped this here, right? So I'm interested there, right? And of course, the dropping mechanism. I might go take a look at FGSM.sys. I might copy, for instance, this over to my desktop. Actually, I'll just put it in labs. Okay, so I now have a copy of this that I might then go take a look at. For instance, here I can come back into my labs directory and grab FGSM and drop it into PE Studio and go take a look at what does PE Studio know about this, right? What can it tell me about this service? Because what I have an idea, or this .sys file, which may or may not be a driver. One of the things that I say may or may not be, by convention, it is a driver, but that doesn't mean that it is actually a driver, right? Although here it seems to indeed indicate that, at least for the few things that detect it as malicious. Notice here, though, a lot of things don't detect this as malicious, right? So kind of the delta that you're looking at here is kind of the payload versus the dropper. This might be the payload versus the thing that we're analyzing the debugger right now being the dropper. Okay, so I got to create service. I'm going to go ahead and run again here and see if we get another breakpoint. Sure enough here, it says no. Let's go run again. Control Shift. No, okay. So this actually is not unexpected. We're trying to start a 32-bit, create a 32-bit service on a 64-bit, 32-bit driver on a 64-bit machine. I'm not surprised that this is causing a violation here. So this malware would have been targeted for a 32-bit machine. We're analyzing a 64-bit, right? Now, I'll tell you that a lot of malware today, and this one's an older sample. It's one of the reasons I grabbed some recent ones. But then we weren't getting immediate targeted findings that I could show you to kind of highlight some of the debugger stuff, some of the debugger theory that we walked through, and hence that's why we're here. So I'm looking here, and we've run about an hour and 45 minutes, right? And so this is a spot where I think is probably a good time to do a wrap up and then leave a couple of minutes for questions, intermission, whatever here at the end. So let's see, a couple of high points, right? One, you don't need to know a lot of assembly to do analysis, to do basic analysis. We've seen here how some Google foo with intermodular calls can get us to at least in some cases. Right? Obviously, you saw some cases where we didn't get good targeted findings. And why didn't we get good targeted findings? That is going to require some deeper analysis and some assembly. I'm sorry. But in other cases, we are able, for instance, to find a mutex name being created. We're able to find registry calls and see how those work. And I'm a big fan of upping your game by learning how to use the debugger. You will not regret again learning how to do this and learning how to get some debugger experience. Hopefully, at least that first piece, kind of walking you through some of the. And by the way, too, you'll notice there's tabs that we haven't even touched here. Right? Normally, when I teach a malware course, I'm a big memory fanatic, memory forensics and memory manipulation in general, and I dive through the memory map and how the paging system. I just don't have that kind of time. So, but I do recommend though that you take a look at really some of these other tabs and the features that are available in the debugger and some of the stuff the debugger can do for you. Because really all we hit, let's see, we hit the CPU pane. We looked very briefly at breakpoints, symbols certainly, and then references. And I think we were briefly in handles, right? But again, there's so much more up here and so many more features to look at. But the other thing I'll mention too is don't be intimidated, right? This is the kind of thing, malware reversing and malware analysis is the kind of thing that can be extraordinarily frustrating to deal with and frustrating to learn. And a lot of people are like, well, I don't know everything about this debugger, so I'm just not going to deal with it. I'm just going to ignore it, right? Kind of thing. I'm not even going to try, right? And it's like, no, get in there, slog through it. It's going to suck initially because it just is. And as you learn more, it becomes this chain learning experience. And generally, folks over time get much better at this, all right? So anyway, that's where I'm going to leave you here. I appreciate everybody's time today, and again, certainly examples could have been a little bit less disjointed. I grabbed again some samples here to samples to walk through. But again, I'll provide a download link to all those samples here as we go live. So anyway, appreciate everybody's time. Thank you so much for coming out. And again, my name is Jake Williams from Addition InfoSec. Peace out.